Thank you very much. So I'm from the University of Southampton, but actually I'm doing a sabbatical at the moment, so I'm in Hawaii, which explains my shirt and the slide. And in Hawaii, they have this thing called Aloha Friday, in which you're supposed to dress up in Hawaiian costumes. So I'm being... So anyway, so I was really excited to be at this workshop, and originally I was going to tell you one particular story, but then during the week I saw so many talks that sort of discussed things that I care deeply about, so then I thought, okay, I'm going to need to sort of broaden out the scope. So actually, the programming recurrence relation stuff is going to be probably about 30 seconds of the talk, but I'm going to spend most of the time talking about other compositional stuff. So there's a whole bunch of people involved in this. So some of these people you'd recognize. So Dushko is actually who I'm visiting in Hawaii. And well, as I'll tell you about these people as they show up during the talk. And unfortunately, I have a lot of stuff to get through, so I don't really like giving these overview talks because you never end up saying anything in any great detail. But I'll do my best to keep you interested. But actually, there is a kind of a common thread for this talk, and it was sort of explicitly identified by John Byers during his talk. And that is, we're going to see a lot of situations in which we're going to have two symmetric monodal categories, one which we're going to think of as some kind of syntax, and one which we're going to think of as some kind of semantics. And we're going to have a symmetric monodal functor from the syntax to the semantics. And this should remind you of Lovier's functorial semantics of algebraic theories, right? It's really the same spirit, except we're not going to typically be in a Cartesian setting, but in a monodal setting, right? Because we want to be careful about resources in many of these examples. And I'll tell you more or less, this is actually a chronologically correct story. So I'll tell you sort of what I've done and what I've learned along the way. Oh, I've got a clicker. So I'll start off with talking a little bit about Petri Nets. And we've already seen some stuff about Petri Nets in John's talk. So what we're going to think about is Petri Nets as sort of open Petri Nets as arrows in a symmetric monodal category. Okay, so the idea is that we have a Petri net that looks like this, which is, in this particular example, this is some kind of a token ring network. Okay, and you see that when you look at it as a sort of a global monolithic net, sort of when we look at it as humans, we can immediately see that it's just three identical bits wired up together in a loop. But we need an algebra of these diagrams to bring this out. So in particular, I'm going to actually be able to write this guy as an expression in a symmetric monodal category, excuse me, which you can see, I mean, it features things like cups and caps and identities, and it has bits which just look like Petri nets that sort of connect to the boundary. And I'm going to try to convince you that this point of view is not just sort of interesting for its own sake, but it can actually be useful. So we have some results about using this for verification, sort of compositional model checking, which came up in several talks, but also things like parametric verification. So maybe I should start by saying something about compositionality in Petri nets in more generality and maybe the history of it. So Petri nets are not often thought of as compositional, but actually there's been a lot of work on looking at sort of the algebraic structure of nets. And there's sort of, the way I look at it, there's really two different ways you can think about compositionality in Petri nets. So one way is you can think about the computations as having some algebraic structure. Okay, so there's a classical paper by Hugo and José Messeguer, Petri nets and monoids, in which they actually considered the computations of Petri nets as a symmetric monodal category. And this inspired a lot of later work. It was a very influential piece of work. Now, the other way I see compositionality as occurring in Petri nets is you think of the actual combinatorial structure of a Petri net as some kind of a hypergraph, and you want to split it up into components and stick together. And again, there's quite a bit of work on this. I'm just going to flash up two of these. So one of them is this approach called Open Petri Nets, which was done by Paolo Baldan, Andrea Corradini, Hartmut Ehrig, Reiko Heckel, and a number of other people. And here, the idea is that we glue together nets along places. So places of the net are the boundaries. And this really reminds me of Blake's approach that we saw earlier in the week. But so I guess the interesting thing about Blake's approach is that he considers stochastic mass action semantics, and it's really interesting. It seems to be really sort of a testament to the naturality of this kind of algebra, that this is compositional, right? So it's compositional with respect to this stochastic mass action semantics. But what I want to talk about in a bit more detail is this approach that I was involved in. And this idea is that we're going to glue together nets along transitions. So just like in this picture here, you see that here we have a single transition which loops around, and we've sort of divided into a number of chunks here on the right. And it sort of all glues together as one transition. And the way I think about it actually is that sort of these transitions that connect to the boundaries, you can think of them as synchronizations of which you have a local view, and you'll only have a global view once you compose everything. So it's some kind of a, I'm involved in the synchronization. I know what happens to me internally, but someone else will synchronize with me eventually, and there'll be other stuff happening. Okay, so since we want to stay within this framework of giving symmetric monoidal functors, I'm going to tell you about the two categories here involved. Okay, so one, unfortunately, we already had one category called Petri. This one I'm also going to call Petri. So this is going to be our syntax, okay, and this is going to be our semantics. And the fact that this is a symmetric monoidal functor is where all of the action will come in when we do things like divide and conquer and compositional verification. Okay, so first of all, I'm not going to give you a formal definition, but I'll just give you a bunch of examples of how composition works in this category of Petri Nets, right? Because I think this is is going to give you an intuition for how these things work, right? So the idea is that sort of arrows in this category, so this is an arrow from 0 to 2, and you see we have the ability to connect transitions to the boundaries. Okay, so here, for example, this is a transition connected to the boundary. This is another one. When I compose, they glue together in a single transition. Now you can have some slightly strange artifacts. If you just come from Petri net theory, you might think they're a bit weird. So for example, you have a transition that's actually not connected to anything apart from the boundary. But what this means is essentially that this piece here, there's a synchronization that I'm willing to participate in that just won't have any effects on my local state, right? So essentially, here when we compose, this just becomes a transition that produces a token at this place. So maybe I'll just go through these very quickly. I don't really have time to get into the details. But you can see that some other interesting things can happen. So here we have a Petri net in which we have two separate transitions, but actually I can connect it with this strange transition here, which is connected to both of the interface ports. And those two transitions that originally we didn't know they were the same synchronization now become the same synchronization, and this just becomes a transition that consumes a token and produces one here. So here's another interesting little feature. If I have a transition connected to the boundary and I have nothing for it to synchronize with, well, that transition disappears, right? We need to be able to find a partner for our synchronization. Or maybe I should say one final thing. This is somehow where choice can come in, right? So here we have two different transitions connected to the boundary. They can both synchronize with this guy here on the left, and the end result is you have two synchronizations, two transitions in the result. Okay, so I hope this, of course, you're not going to get the full picture, but the basic idea is that we want to think about Petri nets as string diagrams, right? And there's rules on how to compose these things. So that was the syntax. Now what's the semantics? Well, if you know about this work of Bob Walters, he has this thing called the algebra span graph of transition systems. then you already know what the semantics is. But if you don't, then I'll just give you a very quick intuition for what these things are. So the arrows are going to be certain transition systems where each label, each transition is labeled with two things. Okay, and these two things depend on the boundary. Okay, so this is an arrow from 1 to 1, and that means that every label will consist of one symbol on the left and one symbol on the right. Okay, so the idea is that when this transition happens, we can observe the action 0 on the left boundary and the action 1 on the right boundary. So there's two ways. This is a symmetric monoidal category, so I need to tell you how to compose and how to do the tensor product. So I compose, so this is the composition of f and g. So I compose by, it's kind of like a product construction, but I need to make sure that I agree on this shared action on the boundary. Okay, so for example here, I can do a 0, 0 action from this state to itself, because here I can do a 0, 1 action, and here I do a 1, 0, and you see I agree on this common boundary, that gets thrown away, and I'm just end up with the 0, 0 action. Okay, and so it's kind of like an algebra of synchronization of transition systems. So what happens when I tensor? Well, essentially I just take the product of transition systems and I just concatenate the labels, right? Because we want to keep this intuition that, you know, tensoring is putting boxes on top of each other. So when I put boxes on top of each other, my boundary grows. Okay, and these things are not connected. So essentially I just take the product of the transition systems. Okay, so now there's a functor that gets me from my string diagram symmetric monoidal category of Petri nets to this semantics. Okay, and that essentially tells me what the internal states of this net subcomponent are and how it interacts with the outside world. And you see that essentially the reason for why the alphabet is just zeros and ones is because if a transition fires, that's a 1, that's kind of like a signal I'm synchronizing. Odd label is 0, which means I don't see any action on the boundary. Okay, it turns out that this square is commutative, which just means that, well, it's one of the things that you need to verify that this is actually a symmetric monoidal functor. And this is really where so looking at this diagram, I can give you some reasons for why this is useful for verification. You see, because I'm composing sort of this big net made out of pieces. And when I want to verify it, this is what I'm interested in, this big, you know, transition system. So the idea is that if I know about the compositional structure, if I know about how this guy is wired up from simpler components, then I can take advantage of this information and do some simplifications along the way to these component transition systems, throwing away maybe some useful information about the internal computation of a particular chunk to get, you know, to get improvements about the thing here. Okay, so we have a paper and we have a tool. So unlike Jamie and Ross, I'm not going to show you my tool, but you'll just have to believe that it's very good. So we actually use two tricks. For some reason, both of them appeared at Pawel 2013. So one is about sort of minimizing automata, and one is about checking NFA equivalence, because we use dynamic programming when we sort of construct these large transition systems. And well, this is you know, we did a big table of experiments, and of course we beat everything. You know, I have to say, I mean, it's a little bit cheating, because traditionally, in this community of verifying Petri nets, you're given the global Petri net to start with, right? So you're supposed to verify the global object. And we cheat a bit because we give the decomposition information that we pre-compute beforehand. And actually there's some really interesting semantic issues that came up earlier in this workshop, and it was the first time I've ever heard anyone say this. Like, for example, things like associativity. You know, associativity holds at the mathematical level, but associativity does not hold at the performance level, right? So some ways of associating your term can be much quicker than other ways. So we sort of do all of these things beforehand, and then of course the tool runs very quickly. So So there's a whole bunch of papers. I should say that, okay, Owen Stephens was my PhD student, and he graduated last year, and he wrote a really nice PhD thesis about this whole idea of, first of all, this composition algebra of Petri Nets, and also how you check reachability. And so if you want an overview sort of that gets into the nitty-gritty and the details, Owen's thesis is where to look. Okay, and yeah, so there's been a bunch of theoretical work on this. And we've also tried to kind of discuss this with people from the Petri Net community, and I think we managed to make some headway there. Okay, so that kind of was the first part of the story. And so yeah, so here we had compositionality, and we're able to verify quicker. We're able to do compositional model checking. So now I want to tell you about what happened next. Okay, so what happened next was one of the most surprising things that ever happened to me in my research career. So at some point, I sat down and I thought, okay, I've got this kind of a combinatorial description of these Petri Nets as string diagrams, but can I present it as a symmetric monodal theory? Okay, so I've got these Petri Nets. I want to present it as a symmetric monodal theory. And the way I was thinking about it was that sort of there's two ways. If you look at a Petri Net as a hypergraph, there's two ways that multiplicity comes in, right? So first of all, a transition can connect to more than one place, right? So you have these transitions that sort of, for example here, this guy is a synchronization that just says, I want to synchronize all 3 ports on the boundary. And it turns out that when you look at the way we did the composition, that this guy has a co-unit, this guy is just the same guy reflected, and this guy has a unit. So in particular, if I just draw them like this, I have a commutative monoid and a commutative comonoid. But there's also another kind of multiplicity that comes in with Petri Nets, and that is that a place can connect to more than one transition. So here I have 2 separate transitions, one connecting this bit, these 2 ports, and one connecting these 2 ports. And then it turns out that this guy also has a unit, and this guy has a co-unit, and this is just the thing without any transition whatsoever, right? Because when I compose, this guy's just going to disappear, and I have the identity left. Okay, so here I have another monoid and a comonoid. Okay, so this started to look promising, so I thought maybe I can write down all the equations. Okay, so first of all, this structure here, which let's call it the black structure. So that satisfies the Frobenius equations and the special law. So far, so good. And when you look at the interaction of these 2 guys, well, they satisfy the bialgebra equations, which we've seen in a bunch of talks already. So the bialgebra equations essentially tell you that the monoid of one color distributes over is a homomorphism of the comonoid of the other color, and vice versa. Okay, so this is looking promising, but then unfortunately the white structure is not quite Frobenius, and unfortunately there's a whole bunch of other sort of complicated things. So I wrote a little bit about this at Calco 2013, but then I thought, okay, it's just a little bit too ugly. What if it was just the most beautiful thing that one could think of, right? What if the white was also Frobenius? So we had this black Frobenius, white Frobenius, and together they were bimonoids. And at the same time, Fabio Zanazzi was studying his PhD thesis. So I was in Lyon, and sort of we're talking about Petri Nets, but then we drew these equations on the board, and we thought, what is this thing, right? So it's not Petri Nets, we know, but what is it? So this is what we wrote down, and we're kind of thinking, what is this thing? So eventually, Fabio visited me in Southampton, and we figured it out. And I was very excited, and actually, this is a bit embarrassing. I put it on Facebook, right? We together with a picture of all the equations, say, oh, wow, this is so nice. And then the next surprising thing happened is that Bob wrote to me on Facebook saying, hey, I saw your post about the graphical calculus. This is actually a fragment of the calculus of complementary observables Ross Duncan and I used in blah, 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 which you've seen many times during this talk. It's just the ZX calculus. Right, so if you take the ZX calculus and you throw out the phases, you essentially get this. So this is all very fascinating. I started with Petri Nets, and suddenly I'm talking about quantum computing, so I was very confused and excited at the same time. But actually, we figured out that what this guy is Okay, so let's call it IH. So this is a symmetric model theory. Sorry. So what is this guy? This guy actually is isomorphic to linear relations over Z2. Okay, so it's this kind of a slightly strange linear algebraic object. And in fact, it's part of a bigger picture that we figured out. That here, so let's, again, this is a kind of a situation where we have a symmetric model of functor. This thing is algebraic theory. And this thing is this category of linear relations over the field of fractions, over the rational numbers. Okay, so this is really crazy, right? Because where are the rational numbers here? Where are the even natural numbers, right? It's not very clear at all. So we figured all this out, and actually, this is. So I should say that this is now no longer not merely a functor. This is actually an isomorphism now. So this is really a presentation. It's an isomorphism of symmetric model categories. So this is a presentation. This equational theory is a presentation of this category of linear relations, and you get all kinds of cute things like figuring out that the way we add fractions is just a special case of the algebra of diagrams. And this other cute thing that somehow nothing's stopping you from dividing by 0, and you can sort of figure out where that leads you. So, and overall, I mean, if you think about what this guy is, we have matrices, but we also have kernels and images. So if you want to sort of start doing linear algebra, there's nothing stopping you from doing linear algebra using string diagrams. So I started a blog about this, because I kind of wanted to popularize the thing. I was very excited at the time. And so there's been some nice reactions on social media, etc. So maybe I should explain to you what this thing is, because we were trying to figure out how this whole idea of Frobenius and bialgebra interacting together, how we can understand this in some kind of a compositional way itself. And this came up during Ross's talk. Ross was saying that one source of compositionality would be to try to understand the algebraic theories themselves as compositional in some sense. Okay, and I think one really beautiful example of this, and probably sort of the first paper that took this point of view, was this paper by Steve Lack titled Composing Props. So I don't know if I really want to get into this, into the detail of what's happening here, but essentially what's going on is that this is a cube in which the top face, they're all sort of syntactic entities, right? They're all algebraic theories. And at the bottom, we have these kinds of semantics, right? So this is the theory of Hopf algebra, and over some principal ideal domain, and it presents the symmetric model category of matrices over that principal ideal domain. So the interesting thing is that we can use this framework of distributive laws introduced by Steve to obtain equational characterizations of the category of cospans of matrices and of the category of spans of matrices. So all of these things are isomorphisms, right? Now, if I look at the top face, these are algebraic theories. So what happens if I take the push-outs? Well, all of these guys share the same signature. So essentially, what you do is you just throw all the equations together. You throw in the equations you get for cospans and spans, and you get this isomorphism here of linear relations over the field of fractions of R. So you have to do a little bit of work down here to convince yourself that this is a push-out and the category of props. But anyway, this is the way we get this kind of a general story. And if you want a really nice source for understanding how this works, Fabio Zanazzi's thesis from last year also is probably the place to look. Well, I'm actually doing okay, so I guess I'm talking very quickly. Okay, so that was the kind of a story about compositional linear algebra, which sort of came out totally by accident, really, because sometimes you just kind of follow your nose and think about what happens if the world was slightly more beautiful than it really is, right? And linear algebra comes out. Okay, so I'll tell you about one application of this thing, and this is about doing signal flow graphs. Okay, so signal flow graphs are quite well known in control theory and engineering, and they were actually invented by Claude Shannon in this paper that nobody knows about, called The Theory and Design of Linear Differential Equation Machines. And I think the reason why nobody knows about it was it was classified for quite some time. But it's a very nice paper. And the idea is that these guys were trying to, I don't know, make the cannons aim better. So they were constructing circuits from adders, gearboxes, shaft junctions, and shafts. And this whole idea was this was some kind of a way of solving, sets of constant higher order differential equations. So how do we get to this? Well, this general picture that I showed you before, it starts off with you having a principal ideal domain. So one good source of principal ideal domains is to start with a polynomial ring. Okay, so by doing this thing that we had on the previous slide, in the cube, we essentially get a presentation of the category of linear relations over the field of polynomial fractions. Okay, and it's well known, this goes back now to sort of more than 100 years. In combinatorics, people often write polynomial fractions as a nice finite syntax for infinite series. Right? This is called generating functions, the theory of generating functions. And the way you can understand this is you have a field embedding from the field of polynomial fractions to the field of Laurent series. So Laurent series are these formal power series that start at some finite time in the past and go possibly infinitely, well, they'll go to infinity in the future. Okay, so here we have an isomorphism of categories embedding us sort of, having our syntax means the same thing as linear relations over polynomial fractions. But we also, because of this field embedding, we have a faithful functor from this category to this category. So overall, we have a syntax for these relations over infinite streams. Okay, so it's almost like circuit diagrams that process streams. And in fact, this is the case. So you can understand the diagrams in this world as an algebra of signal flow graphs. Sorry, this is a typo. That should be Byers. So this is another weird thing. At the same time, we found out that John Byers and Jason Bailey figured out, came up with an equivalent equational presentation. So they have a paper called Categories and Control, and also Jason's very nice thesis, Categories and Control Applied Props, which came out recently. So there's other parts of the story, because we've come from a more computer science background. We're thinking of this as a process algebra, so we thought, okay, we should give this thing an operational semantics that then allows us to sort of compute the action of these string diagrams step by step, and we had a paper last year about this. But since I don't really have much time, maybe let me just sort of tell you the most surprising thing that came out of this, sort of the lesson that I learned somehow. So the interesting thing about signal flow graphs is feedback, right? And the Frobenius structure is the thing here that gives you the compact closed structure that allows you to do feedback. Now, if you look at the way feedback has been understood over the last 100 years, people kind of look at this and they get a bit scared, right? Because there's an input here, there's an output here. What does it all mean, right? So people have been coming up with all kinds of primitive operations and building mathematical theories based on them. Okay, so things like cleaning star in computer science, things like trace monoidal categories. Okay, so this is one way of doing it. There's another way of doing it, and somehow I found it really interesting and rewarding to throw away the directions on the arrows and just think about that inputs and outputs don't exist. Okay, so just throw away causality. And I came across this work of a guy called Jan Willems, who's a very influential control theorist who started something called the behavioral approach in control theory. And he had a whole bunch of polemical papers in which he said, oh, real science is we should not use things like inputs and outputs because they don't really exist in physical systems. It's all a human, it's a figment of our imaginations. And he's quoting people like Bertrand Russell, who wrote things like the law of causality is survives like the monarchy, only it's because it's erroneously supposed to do no harm, but in fact it does. Okay, so we throw away arrowheads, we work in compact closed categories. And unfortunately, this was actually going to be what the talk was going to be about originally. So I took the description of from Fibonacci's Liberabaci of the Fibonacci sequence, right? And he explains it as this kind of a rabbit breeding example. And actually, Fibonacci's Fibonacci numbers are a little bit different to our Fibonacci numbers because they start with 1, 1, not 0, 1, or not 0, 0, 1. So this is the generating function for Fibonacci's Fibonacci numbers. Now, I didn't explain to you how to do fractions with string diagrams, but when you just take this and draw it as a string diagram, you get this guy, okay, as a string diagram. So you see it's kind of confused. It looks like, I mean, this is not an input, this is not an input. So if you actually think about the flow of inputs and outputs here, it's not really clear what's going on. Okay, but the interesting thing is that using the algebraic theory of the string diagrams, so looking at this the diagrammatic reasoning, the equational system that I showed you, I can convert this into something that looks like this and into something that looks like this. Okay, so they're all equal in this algebraic theory. But there's something interesting about these two diagrams. You see, this diagram I can understand as input being on the left and output being on the right, and this thing as being a feedback loop. Okay? And with this diagram, I can understand this thing as being an input and a feedback loop here. So here I have an input, here I have an output, here I have an input, here I have an output. So the direction of flow is the opposite, but they describe the same behavior, right? So as a linear, how much? 2 minutes, okay, perfect, I'm almost finished. Okay, so the interesting thing is by looking at behavior relationally, throwing away these notions of inputs and outputs, I can reorient things, and this is the inverse of the Fibonacci function, right? So if Fibonacci wanted to know what sequence of killing rabbits and buying rabbits I have to maintain in order, let's say, to keep 4 rabbits in my rabbit pen at all times, I would just use this circuit here, right? Because it's the... Anyway, so... Okay, so my last slide is, so this was kind of an optional part of the story, so I'll just go through it very quickly. So this is, so in the beginning, God created Frobenius and bialgebra, right? And everything else is just Frobenius and bialgebra interacting in funny ways. Okay, so we've seen so many examples in this workshop. Well, I mean, I'll just go through it very quickly. But we've seen them in quantum, we've seen them in, well, they've actually showed up previously in the work of Ugo, for example. We've seen a whole bunch of them in this talk. The stuff called Cartesian by categories, in which you see this a lot. So somehow Frobenius and bialgebra is a high-level programming language for compositional mathematics. And I have some evidence for what I mean by this. And all this evidence is in this paper from LIX this year with Brendan Fong and Pawel Rapisarda, in which, even though sort of the underlying maths, the maths at the semantic level is totally different, all we do equationally is just we throw away one equation and replace it with something slightly weaker. And we sort of convert these string diagrams from the kinds of semantics that Fabio and Filippo and I considered to something that control theorists consider, which is moving away from streams finite in the past, infinite in the future, to streams that are infinite in both directions. And there's some stuff about rewriting with DPO. So DPO also came up earlier in this workshop, but I think I don't really have time to go into this in detail. If you're interested, I can talk to you about it offline. Thank you very much.
Questions? Yeah. You see we have 3 different versions of interacting half algebras, corresponding to spans, co-spans, and linear relations. Can you say a little bit about how they're different at the level of the presentation?
Yes, so I can tell you exactly how they're different, yes. So it's all about, so this is, the way we get these presentations is through this framework of composing props. Okay, so in particular, if you look at this paper, what Steve Lack does is he gets bimonoids from the theory of spans of finite sets and so spans of finite sets. And that happens because when you take pullbacks of finite sets, you start reading off the equations of bialgebras, of bimonoids, from certain small pullback diagrams. Okay, then you make an argument that actually if you take these equations, it's enough for everything, right? And on the other hand, cospan of finite sets gives you the theory of special Frobenius algebras. And then you take pushouts, and you look at particular pushout diagrams, and you read off the equations. So we do exactly the same thing here, except we're calculating pullbacks and pushouts in the category of matrices. Now, the category of matrices has transpose, right? So once you know what the limits are, you know what the co-limits are, because everything is, you can just turn everything around. So essentially, what happens is these two theories, you get from one to the other by changing the colors. Okay, so changing the colors is related to the transpose operation. And what happens is you get something slightly weaker, right? So you get special Frobenius structure on one of the colors, but not quite. You get a Frobenius structure on the other. Okay. And a few things like this, but they're quite subtly, I mean, they're not very different.
Any other questions? Well, I think everyone's ready for lunch.
Thanks.
We break for lunch and we reconvene at 2 o'clock for a discussion.